Bismillahirrahmanirrahim. Today I am going to present my presentation topic an efficient matrix method for coupled system of variable fractional order differential equations. Before to start my presentation, I want to introduce myself. I am Dr. Kamal Shah, a senior researcher in the Department of Mathematics and Sciences, Prince Sultan University of Saudi Arabia. Before joining this department, I was associate professor in the Department of Mathematics, University of Malakand, Pakistan. Today, I want to present some work related to the variable order fractional order differential equations. My presentation contents are introduction, methodology, proposed problem, numerical result, conclusions. The foundation of fractional calculus was laid by Newton in Leibniz in 17th centuries. The area have many applications in medical engineering as well as scientific engineering disciplines like mechanics, chemistry, viscoelasticity, signal and image processing, etc. The most important properties of fractional differential equation is its non-local nature, while its integer order counterpart is local operators. Similarly, the area devoted to variable order differentiation integration have also got attention in recent times. This area was initiated by Samko and Rose in 1993. In recent times, some researchers have published very valuable work related to numerical and analytical results in this area. In this paper work, we established some operational matrices based on Bernstein polynomial to compute numerical solution to some classes of coupled system of variable order differential equations. The definition of variable order integrations and differentiation is given by let V be integrable functions, then the variable order integral for order theta, which is a function of t, a continuous function, is defined by this integral, provided that the integral on the right exists. Similarly, if a function is continuous, then the variable order composed derivative where the order theta is greater than n minus 1, less or equal to n is defined as, where n is equal to the maximum value of theta of t. Now, we define the Bernstein polynomials, which was introduced by a Russian mathematician Bernstein. Bernstein polynomials are defined by these recursive relations. Bernstein polynomials have many properties. Here we discuss only few. Bernstein polynomials have important implication in the proof of famous Weierstrass approximation theorem. Similarly, every continuous real value function over a closed interval AB can be approximated uniformly with the help of Bernstein basis. Also, Bernstein polynomial over the closed interval 1 play an important role in the description of parametric curve, increasingly used in computer graphics. The product of any two Bernstein polynomial can be expressed by this inner product, which further can be written in matrix form as, where k is equal to m plus 1 represent the dimension of the matrices. In closed form, Bernstein polynomial can be expressed as, and this relation can be further expressed in matrix form as Cm Pm of t, where Pm is the function vector, will be defined later on, and this is the coefficient matrix. Let Pk t of t be the function vectors defined into, then the variable fractional order integration is defined by these relations, where the operational matrices U, K cross K of order theta of t stands for operational matrices of variable integrations and is defined as. This G matrix is already defined, and the V matrix is computed as, where the entries of the V matrices are calculated by these relations. Similarly, if Pk be the function vectors of Bernstein polynomial, then the variable order integrations of the function vector can be computed by these relations, where this is the operational matrices of variable order differentiation, which is defined as the entries of the matrix are defined in the next slide. And here you see that if I is less than maximum theta of t, then the entry will be calculated by these relations. Now, if I is greater or equal to maximum theta of t, then the entries will be calculated by these relations. And now we find some general result for approximation of a function. Let g be a square integrable function over the closed interval 0, 1. Then this g can be approximated in terms of Bernstein polynomial as, where Cm is the coefficient matrix and Pm is the function vector, which is defined as. Say the coefficient matrices can be calculated easily by multiplying this left-hand side by this polynomial and integrating from 0, 1. This is like an inner products. We take from both sides, we take an inner product of VGM, which we get the entries as. Let G be a function whose m plus 1 times derivatives are continuous. Are in other words, G is a function which is m plus 1 times continuously differentiable function, and this is the Bernstein basis. Then if this is the best approximation of G over X, then the error bound is computed as where m is equal to the maximum t belong to 0, 1 close interval gm plus 1 times of t and s is equal to this one. By this relation, we can check the convergence of the procedures. Now to establish two algorithms for two problem 1 whose order is lie between 0 and 1 and the other whose order is lie between 1 and 2, we establish two algorithms where the function g1, g2 are linear continuous function defined as. For problem was we use lemma 5 and 6 and reduce the system 6. We have called problem 1 to a matrix form S. And similarly, by using lemma 5 and 6, in lemma 5 and 6, we have already established two operational matrices after variable order integration differentiation, which reduce system 7 to matrix equation S. Now, using computational software like MATLAB or Mathematica, we solve these systems for the coefficient matrix A, K, and BK. And when we get these coefficient matrices, we put in the corresponding relation to get the numerical solution. To support our finding, we here give some examples. The first example is a coupled system of blood therapy models given in 5. The analytical solution of this problem at theta is equal to 1 order is given as where the function V and W represent lidocaine amount in the bloodstream and the body tissue of the problem. Here we present comparison between exact and numerical solution for coupled system 10 in figure 1. We see that both solutions are very close to each other. Similarly, in this figure, we have presented the absolute error. We see that the absolute error is very, very small because the problem is very smooth and the solutions are closely related. Similarly, here we have presented the numerical solution at various variable order for using scale level 6. Here we have considered this variable order and use the level 6 to compute the absolute error for various values of t. Similarly, to support our problem, we have considered another example. This is a linear example with homogeneous conditions. At theta of t is equal to 1, the analytical solution can be computed as. In this figures, we have presented the numerical results. We have compared exact and numerical solution which are very close to each others. Similarly, we have here computed the absolute error at level 6 for two problems. Here we have presented the numerical solution for some variable order, different variable order is scale level 6. Here we have compared our results with the famous Harvey-Wheeler method at using the collocation point 32 for theta is equal to 1 for example 2. We see that our proposed method have good results as compared to Harvey-Wheeler methods. We see that at scale level 10, our results are more better than that of Harvey-Wheeler being computed for the shared problem in the reference number 6. Here we conclude some remarks on our adopted methods. Our adopted method is sufficient for the numerical solution of coupled system operational differential equation. Also, the proposed spectral method applied to any linear problem has been stable, which has been proved in this reference 7. The accuracy rate of the developed algorithm is higher for the numerical solution. The proposed method gives good numerical results for the considered problem as compared to Harvey-Wheeler method solutions for the mentioned problem. Accuracy of our proposed method can be increased by increasing the scale level because the method is oriented to scale level. No need of prior discretization or collocation like Harvey-Wheeler methods. In our method, does not need any prior discretization of data. We Here, these are the references we have used in our study. And this research work has been supported by the Prince Sultan University through the research lab task. Thank you.